and the silica gel partially inside the fuel cell. The assembly.
Really? A nuclear accident involving those stupid little bags? Today we're going to be looking at another one of Plainly Difficult's videos. Specifically, the Czechoslovakian nuclear reactor that kept having accidents. Glad I didn't work there. For those of you who don't know me, I'm Tyler Folse. I'm a nuclear engineer with a little over 10 years of experience in the commercial nuclear power industry, from engineering to operations to emergency response. I don't claim to know everything there is nuclear, but I can certainly share some knowledge. Let's see.
It is the 17th of May, 1979, and the government is deciding to close down.
So shortly after 3 Mile Island, that was in March of 79, but well before Chernobyl, okay?
A nuclear reactor is not particularly old, having only been in operation for a little under a decade. It was certainly not cheap, so throwing away an insane amount of investment was not a decision made on a whim. But much like a car with a blown engine, sometimes it's better to just cut your losses. And this is exactly the case with Bonicia A1 in the Czechoslovak Socialist Republic. In just a few short years, the reactor had proven to be a disaster, with 2 operators losing their lives and 2 major reactor incidents within just 2 years. As such, closing the place down is not such an unreasonable reaction. The latter of the 2 events will be rated on the INES scale of a 4, putting it in line with such events as the Tokaimura nuclear accident, Volusian's reactor meltdown, and the famous SL1 disaster.
Okay, so he's talking about the INES scale. Not my favorite method of classification. So here's what it looks like. The main issue I have with it is it's mainly to do with the area of effect rather than the severity of the effect. Here it is more detailed. So SL1 and Tokaimura had fatalities, and as Plainly Difficult said, were classified as 4, but it was localized. Compare that to, say, 3 Mile Island, which is level 5 and had 0 fatalities, and it was largely overblown and everything was safely contained, but was classified higher. And infamously, you see Fukushima classified at the same level as Chernobyl. And I'm talking about the nuclear accident part. I'm not talking about the earthquake and tsunami. With Chernobyl had dozens of direct fatalities, and possibly into the thousands if you look at increased cancer rates over several decades. But Fukushima, only 1 confirmed fatality, and yet it's classified at the same level. So I know that's not the only thing that feeds into these scales, into this scale, and the scale is really about the level of countermeasures that needed to be implemented by local versus international organizations. But I don't like it where accidents with fatalities are ranked lower than accidents with 0 fatalities.
Unlike those, our ones today were just not mentioned to the public, thus got largely forgotten to time. Today we're looking at the 1976 and
That's the other thing. The classification scale has been amended over time. I don't actually recall. That particular chart did not exist in the 1970s.
1977 Jaslovsky Bonicia nuclear power plant incidents. My name is John and welcome to Plainly Difficult.
Nice jingle.
Nuclear state. Our story begins in the 1950s. The Cold War between East and West is well underway. Europe has been divided. One country which has found itself under the communist banner was that of Czechoslovakia. The country in 1948 had experienced a USSR-backed coup. The country proved to be a little nice addition to the Soviet sphere of influence. It bordered West Germany and, vital for our story, had a large number of uranium deposits, as said in Nuclear Energy in Czechoslovakia, an outline and description of its development trends. Czechoslovakia was well stocked with uranium, whose deposits were 6 to 20 times larger than the world average. Uranium had been regularly shipped to the USSR from the late 1940s, understandable as it would make a portion of the uranium used in the Soviet Union's first atomic bomb.
It's fascinating to me how a resource that a couple decades before was thought of as relatively unimportant or even unknown by most companies, governments, key decision makers, And yet, once nuclear power became a thing, now everybody wants it, or at least everybody did back then.
As part of the country's first 5-year plan post-communist takeover, a document was drawn up called the General Plan for the Development of Energy, in which it was agreed that a significant increase in power generation in the country was required to reach its economic and production targets.
I've always thought these 5-year plans were especially ironic about rapid industrialization and modernization, often at the cost of human life, with these aggressive targets. Another widespread famine, especially involving the government seizing things. And this was to create a classless society in line with the teachings of Karl Marx. I don't know, I can't make sense out of it. Basically, the government wanting more stuff.
To meet the demand, multiple coal generation stations were built. But after the 1954 opening of the USSR's first nuclear reactor in Obinsk, energy courses would change for the CSSR.
I mean, nuclear replacing coal is a good idea, as coal does supply a lot of baseload power, and so does nuclear, though it's a lot cleaner and more sustainable. Though I don't know if sustainability was one of their targets then, just wanted more energy sources to go with the rapid industrialization.
In 1954, the USSR began to offer assistance to the various states under its sphere of influence, and this was for the research and use of nuclear energy. The CSSR would enter a deal with the USSR on the 25th of April 1955 to share nuclear information. This was followed in March 1956 with another agreement, which allowed, in July and August of the same year, the first group of Czechoslovak designers and constructors, together with Soviet experts, to begin to plan a new and exciting reactor for Czechoslovakia.
I mean, all in all, this part at least sounds exciting. You know, technology sharing. Hey, Czechoslovakia has an abundant resource that can really drive human progress, though it wasn't all sunshine and rainbows.
Which ultimately led to the commencement of the construction of A1 in Jaslovetsky, Bonesia, based in western modern-day Slovakia in 1958. The new reactor, which would be built entirely in the country by Skoda Works, yes, that Skoda, albeit to Soviet plans. However, construction would be mired with economic and technical issues, which would drag out for completion
like any other first of kind.
A1 until 1972, 16 years from start to finish.
That's a mess.
The reactor was designed to be fueled by unenriched uranium mined within the country, and when at full electricity production capacity, it had...
Okay, so unenriched, so natural uranium, where the fissile material uranium-235 is well below 1%, compared to the 2 to 4% range you see in typical civilian nuclear power plants. Now, in order to do that, you're going to have to you're going to need more neutron moderation, as in basic light water is not going to cut it. So they either used heavy water, graphite, or both. Let's see.
A nameplate of around 150 megawatts. This was from 3 turbine generators.
Though not surprising, considering you're doing first of kind, you start off with something relatively small, 150 megawatts. 150 megawatts is going to be comparable to a coal power plant of that time period anyway.
With a stated power of 50 megawatts each. The electricity was then squirted.
Wow, those are small turbines. I mean, look at them, you can see that, you know, the railing for scale of a person standing up, at least compared to a modern nuclear power plant, where the plant I worked at was upwards of 1,400 megawatts on the grid, and that's just one turbine. And the reactor itself was over 3,850 megawatts. So with that in mind, if he's talking 150 megawatts electric, the reactor itself was probably have been on the order of 450 megawatts thermal, just due to a steam cycle efficiency.
Into the 220 kilovolt electric network. But let's have a look at how the reactor worked. The A1 reactor was a gaseous CO2 cooled heavy water moderated system.
Okay, heavy water, and with CO2 as the coolant. Interesting they didn't use heavy water as the coolant.
Reactor core was within a pressure vessel made up of 15
Okay, so I can understand the reason for unenriched uranium, as in brand new design and new nuclear industry to Czechoslovakia, as in we don't want to build an enrichment facility. We want to be producing power right off the bat. Though that's about where the advantages end. CO2 cooled, not as scalable. I mean, you could, but it would probably not be the most cost-effective way, hence the smaller reactor design. And it's weird that it's using the heavy water as just the moderator. Like, the water might as well be sticks of graphite. And you still have to enrich the water to make it more deuterium heavy than the typical light water that you drink and use for anything else. Can-do reactors in Canada use heavy water, but they also use it as a coolant. And they can also use natural uranium. Industry slang for that is dirt burners, because you can just take the uranium right out of the ground. You don't have to enrich it. I mean, you still need to process it and make it into fuel assemblies, but it's just industry jargon.
Centimetre thick carbon steel in a cylindrical shape, with a diameter of 5.1 metres and a height of 20 metres. Surrounding this whole arrangement was a water tank forming the biological protection. The reactor produced power by heating up the coolant CO2 gas.
Interesting. So pillars of water for that instead of using concrete as your bioshield. And by that he means just an additional layer to slow down the neutrons. Just an additional layer to stop the neutron from leaving. Problem is it's less of a robust material. So no primary shield wall. It's less of a shield and more of a aquarium.
It exited the pressure vessel via pipework at a temperature of around 420 degrees centigrade, aided by a turbo compressor which then made its way to 6 steam generators which then pushed the turbines which created the tasty electricity.
Tasty. Okay, so those temperatures are a little warmer, but not unheard of for a gas-cooled reactor. A little warmer relative to, say, a standard pressurized water reactor, which in the 1970s was more or less everybody's thing.
Core had technical channels in which the fuel rods could be inserted. The system's fuel rods were made up from 70 metal uranium wires, each clad in a compound of magnesium and beryllium bundled together. The reactor was placed within the reactor building in which top the biological shield. This was the floor, with a large open building above it called the hall. The hall housed a refueling machine.
Okay, where is the containment vessel? Do they not have one? Is this kind of like Chernobyl in that regard? Because this isn't filling me with confidence here.
Arrangement allowed operators to walk around in the hall without the fear of getting a little bit glowy. Fuel was delivered in the form of
I mean, that's what the water's for. I mean, and there is at least some layers of steel and concrete, so that's not an issue. The issue is if, a pressure transient or the vessel ruptured. The point is there's just less layers, there's less barriers from the fission products to even the workers. So at the nuclear power plant I worked at, there's 3 fission product barriers. The cladding itself, the cladding that surrounds the fuel. Then there's the reactor coolant system, and then there's the reactor containment building. Here, would assume that any fuel type you're going to have cladding, whether your uranium's enriched or not. So they obviously still have that. The vessel, though, in the reactor coolant system seems less shielded. There's no the bioshield is water tanks. And I'm not talking about just radiation shielding. I'm talking about against pressure transients like blast shielding. It's just less so. So they probably get like half a point for that. And as far as reactor containment building, they're not getting any points for that. So in terms of protecting guys within the plant, this is half as effective as best. This is half the barriers, if even.
Uranium rods via rail in special containers. After arriving, it was assembled inside a designated area workshop near the hall.
Also assembling them on site. Usually fuel is assembled at a different location and it arrives at a plant already pre-assembled. But nuclear is new to Czechoslovakia at the time, so they're trying to do what they can in this new facility. I think this is clearly more of an experimental proof of concept to see, let's see how nuclear power works in Czechoslovakia before they start building dedicated facilities.
The design of the reactor allowed fuel changes to be undertaken whilst it was still in operation. This is a great feature as it stops downtime.
That is a good feature. So no need for refueling outages, though you're still going to need outages to do maintenance on, say, your turbine, for instance. Though with 3 turbines, you could just reduce power rather than doing a full outage, but there's still probably going to be some components that require an outage. But the point is, you don't have to do outages as frequently, which is nice. The CANDU reactor has a similar process. I know a few guys that worked at CANDU plants kind of called it doing it rotisserie style. Called it doing refueling rotisserie style. Just take some you take a skewer of fuel out and then you put another one in.
But the whole reusing crack would turn out to be a bit of a thorn in the reactor's side.
Ooh, now that's not
used
today.
1976. So today is a bit of a double disaster special. The first of which brings us to 1976 and the need to refuel the A1 reactor.
So before...
It is January the 5th, 1976, and the reactor is in cooling down mode after a fault has been discovered along the 220 kilovolt power network. The blackout.
So 220 kilovolt, that's the off-site power source, the switch yard, if you will, for the... So you have the main turbine, let's just say it has output voltage of, say, 20 kilovolts, and then it goes to the main transformer, which steps it up to 220 kilovolts or what have you, to put the power out on the grid for long-range transmission, and then it gets stepped back down before it supplies whatever city it's supplying. So basically an issue with the switch yard or the transmission lines or something like that caused the fault.
Occurred on January the 4th, 1976, and this was from a nearby substation.
That
the
makes
reactor,
sense.
during this incident, had been scrammed, that is, having the control rod shoved into the reactor core, shutting it down safely. A fuel rod in channel H05 was planned to be...
So I'm used to referring to that as a reactor trip. Scram is also fine. Old joke, it stood for Safety Control Rod Axeman. Haven't heard that one confirmed, but point is, all control rods safely inserted all at once, shutting down the nuclear reaction in a matter of seconds.
Replaced. It had reached the end of its useful life.
Sure.
In order to replace the fuel, the refueling machine was moved across the reactor hall and placed over the technical channel. The refueling machine was then connected to the technical
refueling
channel,
during an outage.
in doing so matching the pressure within the reactor. The spent fuel rod was extracted from the core into the refueling machine, in which afterwards the tightness of the plug at the top of the reactor was checked. The spent fuel was then moved off to the spent fuel area, and this was at around 11:55 in the morning.
The spent fuel should be stored within just another body of water to absorb the decay heat, absorb the radiation, and minimize overall exposure.
The refueling machine then went to insert a new rod. After apparently being sealed, which was indicated to operators by an electrical indication, the refueling machine began to lift away as per the operating instructions. In an instant, at around 11:57 AM, the fuel rod shot out of the reactor, multiple meters into the air of the reactor hull.
Damn.
The shift engineer at 11:58 AM raised the alarm and called the workers in the reactor room to leave. There was also...
That's what's called a rod ejection. Fortunately, at least now, I don't know about back then, as far as shutdown margin goes, you assume there's enough control rods that the reactor is shut down such that even if the highest...
though a dosimetric signaling of exceeding the permitted values of air contamination.
That's pretty
CO2
radioactive.
analyzers.
And it's not getting slowed down by water or anything. And, wow, the idea that it would make itself out onto the refueling area. See, to me, that's just different because, again, the reactor is in its own separate containment building. So basically, if such a thing were even possible, it would be stopped by the reactor building. It wouldn't shoot out into the refueling area. That's a mess.
Showed an increased concentration in the air, and the hissing of coolant alerted workers nearby to the deadly gas that was now spewing out into the hall. With the reactor now losing coolant...
Oh yeah, that's right. It's carbon dioxide. Oh, so add not just high radiation dose, you can add your toxic CO2. to the kicker here as well. Ooh, that's a nasty twofer.
At a rate of 70 kilograms a second, the unit was in a very real possibility of overheating, leading to a radiological disaster. The heat in the core was rapidly rising, and due to the reactor being shut down from the earlier power grid blackout.
Okay, what kind of safety emergency core cooling do they have? Is it safety injection? I mean, it's normally gas cooled, and the gas is leaking, so
Not enough electricity was available to pump the coolant. The site's diesel generators started
because it's loss of offsite power. Okay. Now, the diesels should, in a modern reactor, they would do what it's known as a mode 3 sequence. Mode 1 is safety injection. Mode 2 is loss of offsite power. And mode 3 is, well, 1 plus 2. Prepared to handle both. Let's see how this works.
up to push the coolant through the core. However, some of the turbo compressors failed to start, thus stopping the flow of the coolant. If the technical channel couldn't be closed, within half...
I've heard, this was, well before I was even alive, but diesels back then were not necessarily the most reliable pieces of equipment. Nowadays, they get tested quite routinely.
Half an hour of the initial leak, potentially all of the gas could have escaped from the core, leaving no chance for the reactor to cool down. After entering the hall in protective gear, an operator managed to move the smashed up fuel rod and was able to manually seal off channel H04, with the help of the refueling machine sealing off the leak. At 1:04 PM, the compressor finally succeeded in reaching the required speed to cool the core. Okay. If a meltdown had occurred, then a lot of people would have known about it.
Especially since they didn't have much of a containment structure here. Man, that's why... You see, that's why, going back to the event thing, that's why 3 Mile Island wasn't that bad, is because it involved a meltdown, but there was no breach of containment. So, I know a lot of people throw down meltdown as the big scary nuclear thingy coming to get you. That's not necessarily the case. It's a radiological release. I mean, that's literally what it means, is it escaping containment and making its way into the atmosphere.
But no one was irradiated and no radiation was released. All the people within the reactor escaped. However, 2 men in an adjacent building were suffocated by the release of the coolant. They hadn't heard the emergency alarms.
Wow.
Surprisingly, there wasn't massive amount.
And that's actually not that unheard of for not hearing the alarms, because a lot of these areas are high noise areas. At the plant I worked at, there would not only be alarms, but there would also be flashing lights that go off that alert of radiological hazards, chemical hazards, and if an announcement is being made, meaning leave the high noise area and heed the instructions.
To damage to the reactor from the incident. The cause was not completely understood. However, steps were taken to avoid the event from happening again. One such was stopping H05 from being used for fuel and adding extra checks during refueling for channel plug seals. The reactor was brought back online after the repairs, but disaster would strike almost exactly a year later, 1977. Our next disaster kicked off on the 22nd of February 1977, with the planned replacement of a spent fuel cell in the reactor in technological channel C05. The exchange was to take place in the afternoon, and as usual, whilst the reactor was operating. It was producing at the time a power output of 93 megawatts. The new fuel rod slid into the reactor and all seemed well. However, shortly after, the operators noticed an increase in temperature in channel C05. The heat damaged the channel to the point that it melted the wall between it and the heavy water moderator. On top of this, the surrounding technological channels also began to experience damage. The heavy water began to penetrate into the gas part of the primary circuit. This meant that the reactor was now running in a dangerous scenario. The separation between the moderator and coolant was now compromised and the heat continued to rise.
So, depending on the exact numbers, you could have... Okay, so that's a loss of coolant accident right there.
Radiation was released into the reactor hull. Quickly, the reactor was scrammed, shutting it down, but the damage was done. Both primary and secondary cooling circuits had been damaged, as well as multiple technical channels.
Okay, where's your safety injection?
Monitoring of the radiation released.
You see, that's another thing, is radiation gets released right into the refueling area. That's why you need containment, because it's like loss of coolant accidents. Okay, the reactor The worst thing that realistically happens is the reactor containment building becomes a hellish environment. But that's why it's called the reactor containment building. And safety injection all fires up and keeps the core cooled, covered, and properly reactive. So they needed a containment building.
Found that the leakage into the environment was not significant. Apparently that's what they said at the time. But how did the fuel heat up from a relatively normal refueling
Wondering if there was some covering up involved.
routine? Well, unlike the first incident, this time it was down to operator error. You see, during fuel transport, silica gel is placed amongst it to stop moisture building up, much like when you buy any electrical item. Workers, when unpacking the fuel ready to be put into the fuel rod, were meant
Don't tell me they saw the do not eat packets and ate the packets.
to remove and discard the silica gel. However, during this, a bag was torn and the silica gel partially inside the fuel cell. The assembly
Really? A nuclear accident involving those stupid little bags? I can't even.
workers managed to partially remove the grains of silica gel with tweezers and a vacuum cleaner, but not every part was collected. They did not record the incident, thus no one knew the potential risk of the mislaid gel.
So that also creates a foreign material exclusion event, the foreign material being a foreign material exclusion event, or FME event. Basically the silica gel being the foreign material that ends up in spots where it shouldn't be and causing an accident.
When the fuel cell was inserted into the reactor core, the gel reduced some of the flow of the coolant, thus allowing the core to overheat. Although the reactor was shut down, over the next 2 days the discharges from the ventilation stack were up to 3 times greater than the daily limits.
Oh yeah.
Even worse,
Not surprised.
in the first week after the event, the
Without
activity
containment.
of discharged wastewater exceeded the allowable amounts by up to 5,000 times into the Deva River. But such a small mistake had long-reaching ramifications, not just for the environment, but the reactor as a whole. The aftermath. Faced with a massive bill for repair, the CSR
Alright, I'm glad this thing got shut down because it was not a good design.
decided maybe it would be best to cut their losses.
I'm also glad they didn't build one of these at scale. I'm not actually sure it would have worked at scale, whereas you would just multiply the amount of energy involved, the amount of potential release involved. Yeah, it could have been even worse.
And shut the whole job down and decommission the A1. The reactor had been nothing but trouble, and the 2 major events were the last 2 very big nails in the coffin. Plus it would turn out to be easier to install Soviet VVER reactors. They boasted a power output much higher than the A1, and with the wealth of knowledge from the USSR, they would be cheaper to operate.
VVERs are basically Soviet pressurized water reactors, which are closer to the plant I worked at.
Over its short life, it worked for 19,261 hours, generating 916 gigawatt hours of electricity.
That's not very impressive for nuclear power. It's really not.
Decommissioning would take, well, is still being undertaken right now, and during the 1990s the fuel was exported to Russia for disposal. But although shut down, the plant has left its mark on the environment. As stated in Wild Plant Species in Bio, indication of radioactive contamination sites around the Jaslovsky Bonasia nuclear power plant in the Slovak Republic. The 19-kilometer long banks of the NPP wastewater recipients
Cesium-137,
have been
of course.
identified as contaminated by Cesium-137.
So that has a half-life of about 30 years. It's a beta source, well, mostly, also gamma source, and probably one of the more significant radioisotopes that lingers after a radiological accident, because cesium-137 is a common fission product. And considering this happened in the 1970s, it's gone through well over 1 half-life, but a fair bit less than 2, and the most radiation protection experts consider something to be gone after 7 to 10 half-lives. One common misconception is 2 half-lives means something's gone. That's not at all the case.
In total, more than 67,000 cubic meters of riverbanks have been found to be contaminated at levels exceeding 1 becquerel of cesium-137.
So 1 becquerel is a pretty small number, but it is elevated and it can quite easily be fingerprinted to a nuclear accident.
This was back in 2007. But as we know from other videos, cleanups are
So one
a
half-life.
long and arduous task. So it's time for my scale. It's going to be a 2. Although the 1977 event got the INES scale number of 4. And this is what I've got for my bingo card. Do you agree? Let me know below.
So what it's got? Preventable, badge, safely, company blaming victim, no training. I would argue there's some overly confident official in just within the design of this thing and warning signs ignored, but if he's just talking about the accident specifically, so not taking into consideration the design of this reactor, then yeah, that's it. That's a fair score. Thanks so much for the recommendation, and thanks so much for watching. I'll see you next time.